Section 3.2 talks about trigonometric integrals. So here we're going to be dealing with different powers of sine and cosine, tan and secant, and you could carry on into cosecant, cotangent. The rules follow accordingly. To do that, we need to recall a couple of identities. The first one is the sine double identity. The sine of twice an angle is 2 times the sine of that angle, cosine of the angle. So it would be very helpful when you see sine times cosine, if you divide both sides by 2, to think of that as the sine of 2 theta divided by 2. Just saves you a step. So we know that the sine of twice an angle is twice the sine of theta cosine of theta. That's one identity. But the cosine happens to have 3 identities. Cosine of 2 theta is the cosine square root of theta minus sine square root of theta. That one we really don't use almost at all. Instead, we focus more on those two. Twice cosine square root of theta minus 1, and 1 minus twice sine square root of theta. And we don't focus on those in the sense of when we see cosine of 2 theta, we write twice cosine square root of theta minus 1. We focus on those in the sense when we see a cosine squared. If I solve for this cosine squared, move the 1 over, and divide by 2, that would give me the following identity. And if I look at that sine squared, if I want to solve for cosine 2 theta equal 1 minus 1 sine squared, if I want to solve for this sine squared, if I swap those, I'll be looking at positive twice sine squared of theta equal 1 minus cosine of 2 theta. Excuse me, dividing by 2 will get me this power reduction. So those are really what we need. This, we really don't need much. We need those to derive those if needed. So I need to know this. I must know this and this. Those are called power reduction identities. And whenever I see the sine, cosine, I could write it. It's really not a big deal. You just save yourself a step, but this is a must. And I must know the Pythagorean identities. And it starts with the most famous identity, the sine squared of theta plus cosine squared of theta equal 1. If I divide by sine squared each of those, sine squared over sine squared is 1. Cosine over sine is cotangent, and 1 over sine is cosecant. And if I go back to this, and I divide each of those by cosine squared of theta, sine squared over cosine squared will be tangent, cosine squared over cosine squared will be 1, and 1 over cosine will be the secant. And that's how this works. So I need to know those as well. And do keep in mind, most of the time, I use the fact that sine squared of theta is 1 minus the cosine squared of theta, or the cosine squared of theta is 1 minus the sine squared of theta. Just keep that in mind. Now, whenever I'm looking at power functions, I start with what I know. Meaning, when I look at a problem that has sines and cosines, I say, okay, well, let's see. I see a radical, which is a power function. If I let u equal the inside of that, so if I let, oh, sorry about that, here we go. So if I let u equal the inside of that, du will be negative the sine of x dx. So it didn't register. So I'm looking at the square root of u, and the blue part I could replace by a negative du. That's u to the 1/2. So add 1 to the power. Dividing by a fraction is multiplying by the reciprocal. Replace u back And that's pretty much all there is to it. And do keep in mind that the cosine of x to the 3/2 is the same as the cosine of 3/2 x. Okay, I look at the second problem. We say, look, again, a power function. I'm going to let u equal the inside of the power function. That's how we start. We always try a u sub first if that will work. And the derivative of sine is the cosine of 2x times 2 dx. So here I'm letting u equal the cosine. And I need a cosine of 2x dx. I can replace that by a du over 2. And that would be 1/2. And this integral will be add 1 to the power divided by that. So that is 1 over 16. And u initially was the sine of 2x. And there it is. I look here and I see two power functions, and I'll be thinking, okay, if I let u equal the inside of this power function secant, then the derivative of that would be secant tangent. That doesn't work because I have tan squared. But if I let u equal the inside of this power function, say tangent, that works. If I let u equal the inside of that power function, and if I take a derivative of tangent is secant squared of x dx, and I notice that that works. And this is u cubed over 3 plus c, and that is u was tan of x cubed divided by 3 plus c. Now, it did work on all of these three, the u sub work. What if that doesn't work? Well, we have rules, really, shortcuts. So, first shortcut, whenever you're looking at a combination of sine and cosine, if either of those is odd, save one of them. If the cosine is odd, save a cosine. If the sine is odd, save a sine. If both of those are even, then the only way out is to use the power reduction. Like we said, those are a must. So we're going to start in order. So we're going to start with, let's see. Here we have an odd cosine. So what we're going to do, we're going to take this and split it into cosine squared times cosine of x dx. And the idea is that this is going to be my du. That's always the case. That is, I'll save a cosine and use the Pythagorean identity. And what does cosine squared of theta equal? Sine squared plus cosine squared equal 1. Cosine squared of theta equal 1 minus sine squared. That's this. And if I let u equal the sine of x, obviously the derivative of sine is the cosine. So basically, this is my du. That's always how it works. Whenever they say save a factor, automatically they're telling you what to do. Make that the du. And of course, what do you take a derivative of to get cosine sine, and vice versa. And it works really smoothly. That is 1 minus u squared du. That is u minus u cubed over 3 plus c, and u was the yellow part, so that's the sine of x minus the sine of x cubed over 3 plus c. And that would be my answer. Again, that is what I will take a derivative of to get this. I could show you. We're going to just show this problem. If I take a derivative of my final answer, derivative of sine is cosine. Here, I'll bring the power down, subtract 1 from the power, times the derivative of the inside, which is, those cancel out. I'm looking at a cosine of x minus sine squared of x cosine of x. Factor a cosine of x out. And 1 minus cosine sine squared is cosine squared of x. And that gives me cosine cubed. So I see a combination, whether it's a sine by itself, cosine by itself, or a sine and cosine. So I wanted to start with the problems where you're dealing with each of those individually, then a combination of the two. Well, again, when you see an odd power of those, you say, okay, I'm going to take a cosine of x out. That means that must be leaving me with cosine to the fourth. And I'm going to say this is going to be my du. So I need to get rid of this and say that is getting excited here. I'm gonna say that's the cosine squared of x squared, and I'm gonna say this is cosine squared is 1 minus sine squared of x. And again, I would keep in mind what we factored is my du. So if I let u equal the sine of x, because I know derivative of sine is cosine, you could be off by a sign, by a plus or minus. That's what I mean by a sign. So if I let that be u, I'm looking at the integral of 1 minus u squared squared. And obviously, I could replace that part by simply du. So this is the integral of 1 minus twice u squared plus u to the fourth du. That is u minus 2u cubed divided by 3 plus u to the fifth over 5 plus c. U was marked in yellow, so replace it back, and there it is. And there it is. Now, this is if you have a sine or cosine by itself. I did cosine twice, that's okay. How about this problem? I notice here I have both sine and cosine, and they're both cubed. If I see one of them cubed is sufficient, both, that's even better. So here, I would say, okay, this is how it's going to work. Now, since I played with cosine before, I'm going to take a sine out. I'm going to take a sine of x dx and save that. What that means, that leaves me with sine squared of x, cosine cubed of x, and they're all multiplied. Now, I am aware this is my du, and I know that I must let u equal the cosine of x, because the derivative of cosine contains the sine. Again, you could be off by a plus or minus, that's not an issue. Which means I'm going to come in here and add an extra step. There's cosine cubed of x. I need to get rid of this sine squared and say that's 1 minus cosine squared of x. And now if I let u equal the cosine, I'm looking at an integral of 1 minus u squared, come on, times u cubed times negative du. And this is nothing more than the integral of u cubed minus u to the fifth du. And that would be negative u to the fourth over 4 plus u to the 6 over 6 plus c. And again, remember here u was the cosine, so that is negative cosine to the fourth of x over 4 plus cosine to the 6 of x over 6. Of course, you could write the power of 6 first. It really makes no difference whatsoever. The next problem up, again, Here, if I let u equal the inside of the power function, it doesn't work. If I let u equal the sine, du will be a cosine, not a cosine cubed. Whenever the power on cosine is more than 1, you have to follow that if you see an odd sine or cosine, it doesn't matter here, I see a cosine. So I'm going to write that as a cosine of x dx. I'm going to save that factor. That's going to be my du, which means that must be a cosine squared of x, square root of sine of x. And the next step up is to get rid of that and say that's 1 minus sine squared of x. So recall that this is my du. And we know how that works now. If I let u equal the sine, du will be the cosine of x dx, straightforward. That would be the square root of u, 1 minus u squared, du. And if I distribute that in, u to the 1/2 minus u, 2 plus 1/2 is 5/2. Add 1 to the power, divide by that, add 1 to the power, divide by that, replace u back, and remember u is, in this case, the sine. And there's my answer. Now, what if I happen to have a sine to the 4th? Well, in this case, if I only had sine squared, that's simple. I use power reduction once, and there it is. And maybe I should do that, and then deal with the other case. So if I had, let me see, can I fit it here? If I was looking at the integral of sine or cosine, it doesn't matter. Let's say sine square root of x dx. Now, here's the catch. The only way you could work out this integral is by using the power reduction. And the power reduction states it is 1 minus or 1 plus the cosine. This angle is twice this. And this is 1/2 the integral of 1 minus the cosine of 2x dx. That is 1/2 x minus, what do you take a derivative of to get cosine? The sine. Recall, if you were taking a derivative of cosine of 2x, you multiply by the 2. Antiderivative, you divide by 2. And that's basically it. So if it is a single even power function, that's not that bad. But if it's repeated or raised to a power, I could do this 2 different ways. I could say either this is the sine squared of x sine squared of x, or the sine squared of x squared. It doesn't really matter. That is the integral from 0 to pi. And power reduction on this, that's 1 minus the cosine of twice the angle divided by 2. And now if I distribute that 2n, I'm looking at 1 minus FOIL twice cosine of 2x plus cosine squared of 2x divided by 2. Divided by 4 when you square the 2, right? So the 1/4 I take up front. And with respect, that's an x. What do you take a derivative of to get cosine? The sine of 2x divided by 2. But here we have a problem. I still have this second degree. What I have to do, I have to use the power reduction on that. The power reduction on that is 1 plus, because cosine squared, sine squared picks up a negative, but cosine squared picks up a positive. You notice those two are the same. 1 cosine of double the angle divided by 2, same deal here. 1 time minus 1 time plus. So in this case, it is 1 plus the cosine, and how does it work? You have to double that angle. 2x, if you double it, that's 4x divided by 2 dx. That is 1/4 x minus sine of 2x plus, I'm going to take the 1/2 up front, and that's going to be an x plus the sine of 4x divided by 4 plus c. Of course, you could distribute that in if you want. You could leave it like that on a test. Anything I box is fine. That's going to be 1/8, and that's going to be 4 times 2, that's 8. 8 times, that's 32. And of course, you could combine those two if you like. No big deal. The book does combine those. On a test, once you're done with the calculus, you're in a good shape. Same deal here. I look at this, say, wait a minute. The only way I could deal with, if one of them is odd, it's an easy problem. If they're both even, there's one way out. This is 1 minus the cosine of 2x divided by 2. This is 1 plus the cosine of 2x divided by 2. I notice the top are conjugates. So this is 1/4 the integral of the first squared minus the second squared. Now you could FOIL it if you, you could FOIL it if you want. You'll get this. And again, I have to use the power reduction on this. That is 1 plus the cosine of 4x divided by 2. That will be 1/4. That's an x. That is an x. And that is the sine of 4x divided by 4. And that will be, that's a fine answer for a test. That is x over 4 minus x over 8 minus sine of 4x divided by 32 plus c. You could combine those over 8. 2 minus 1 is 1. And there it is. So the deal here is, when you get to 6.3, they're going to use 3.1 and 3.2. When you get, what did I say? 6? I meant 3.3. When you get to 3.4, they're going to use 3.1, 3.2, and 3.3, and the list goes on. So this is as far as even and odd multiples of sine and cosine. When we get to tan and secant, well, here I'm looking for an odd tangent or an even secant. Odd tangent, even secant. If I see an odd tangent, I'm going to save a secant tangent. That's my du. If I see an even secant, I'm going to save a secant squared. Recall that tan squared of x. So anytime I want to derive the formulas, sine squared of theta plus cosine squared of theta equal 1. If I divide by sine squared over sine squared is 1, cosine over sine is cotan, and 1 over sine is cosecant. If I go back to this, divide everything by cosine squared. Sine squared over cosine squared is tan squared. Cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared. Anytime I save a factor, whatever's left over, I use the Pythagorean identities. So the first problem here, I see a tangent, right? There are no combinations. I say, okay, well, guess what? I know what that is. We memorized that from the previous section. I'm hoping you already got those 3 down, because they're never going to leave you alone. So what is the angle of tangent? That's negative natural log of absolute value of cosine of x, or natural log of secant of x. This author likes the negative. I like natural log of absolute value of secant of 5x. There's a small catch to this. If you take a derivative, you multiply by 5. Antiderivative, you divide by 5. Otherwise, you have to derive the whole thing again. That takes care of this problem. When I get to this problem, I say, okay, well, let's see. If they're both odd, then this rule works. And if they're both even, this rule works, because it says if tan is odd and secant's even. So in this case, I notice there's an odd tangent and a secant. So there is secant tangent. Here, there were only tangent, no tangent secant. I'm going to save a secant tangent. So algebra. If I took that out, I would be left with a secant squared of x. Remember, this is my du. And doesn't it work if I let u equal what? Secant of x du will be, oh boy, du will be derivative of secant tangent dx. And there it is. So this becomes a simple integral with u squared du. And that's going to be u cubed over 3 plus c. And u happen to be a secant of x plus c. And there it is. Okay. Now, cotangent, either you remember from the shortcut, or you could derive it, and let me show you really quick. If you're not certain or you don't remember how this works, then you could do it, brute force. You could say, look, I don't know what that is. That doesn't match anything. Anytime that happens, I convert everything to sines and cosines. This is no powers of sine and cosine. I let u equal the denominator of a fraction. Du will be the cosine of x dx. It worked out perfectly. Natural log of u, and u was sine of x. There. Everybody's happy. I get to this problem, I say, okay, well, let's use that trick. So again, it's really simple to use those, not much to it. Well, here I say, okay, tangent is odd, very good, but there's no secant, right? So save secant tangent, there is no secant there. And sometimes you could have an even tangent and an odd secant, like the integral of tan squared secant to the 5th. So this rule doesn't apply. Anytime that doesn't happen, switch everything to sines and cosines. Tangent is sine cubed of x over cosine cubed of x, and secant is 1 over cosine of x. So this is the integral of sine, okay, that looks like sine 3, sine cubed of x. That's the sine cubed of x. This is cosine cubed. This is cosine to the 1/2. If you take 3 minus 1/2, that is 5/2. Is that right? Yeah, 2.5. And now I say, look, there is a power function. There. Oh, that's cubed. Now I look at this. I say, okay, well, we have, I don't like how this looks. Here we go. We have odd powers of sine and cosine. We know what to do. Save a sine out. That's going to be your, oh my God. That's going to be your du. Well, if I factor a sine out of that, that means there is a sine squared of x okay. And Pythagorean identity, that is 1 minus cosine squared of x over cosine to the 5/2 of x times sine of x dx. Let u equal cosine of x. Du, I already know what that du is. And that's how I started the whole thing. So, if I let this be u, I'm looking at 1 minus u squared over u to the 5/2, and du with a negative. That is negative the integral, and if I split this up, okay, I gotta write slower. I'm trying to, I don't know why I'm rushing. This is negative the integral, and that is u to the negative 5/2 minus 2 minus 2.5 is negative 1/2, and that turns out to be add 1 to the power, that is negative 3/2, add 1 to the power, and distribute that in. You could leave that up there, you could put it in the denominator. U was a cosine. I'll distribute that plus twice the square root or cosine of x to the 1/2, and there it is. Now, I'm looking at an example. I couldn't find one in the book, so we use the top. I want to use the bottom. What if you see an even power of secant? You say, okay, what I'm going to do, I'm going to save a secant squared of t dt. That leaves me with secant squared of t and a tangent squared of t. Remember, this is my du. I don't know how it works. What do you take a derivative of to get secant squared? You take a derivative of tangent. Derivative of tangent is secant squared, which means I have to get rid of that by using the identities. And what does secant squared equal? Again, I showed you how to derive those. Secant squared is tan squared of x plus 1. So if I let u equal tangent, du is secant squared of x dx. That becomes the integral of u squared plus 1 du. That is u to the 4th plus u squared du. Add 1 to the power, that's u to the 5th. Add 1 to the power, that's u to the 3rd over 3. And what was u? U was tan of x. And that's pretty much how it works. If you happen to have those and you know the rules, it's fairly simple. Now, something I said I was going to derive for you, I'm assuming that you memorized that what do you take a derivative of to get 1 over 1 plus x squared inverse tangent? What happened when there's an a there? Well, I need that to be a 1 to be able to use it, so I factor an a out. I factor an a squared out. I take an a squared out of that equation. A squared divided by a squared is 1. X squared divided by x squared. If I distribute this in, I'll get exactly that. And I'll rewrite this as a is a constant, by the way, in case you were wondering. I could let u equal the inside of the power function. And since a is a constant, when I take a derivative of that, that's 1 over a dx. This is 1 over a squared. I put a u there. Dx is what? Is a times du. This cancel one of those. That's 1 over a, the integral of du over 1 plus u squared. That is 1 over a, the inverse tangent of u. And do we know what u was? U was x over a plus c. So the integral dx over a squared plus x squared is 1 over a, the inverse tangent of x over a plus c. It's worth memorizing. Again, it comes up a lot more than you like. And the last problem, I wanted to do a very tricky problem. This is something that gives students a heck of a time. This problem is easy if you know about what to do, and if it's very hard, if you try different analogies, you can get to the answer. I was able to get to it by using combination of sine and cosine and some identities, but it took me, if I remember correctly, 13 or 14 steps. But if you recognize that tangent squared is secant squared of x minus 1, then this is a very easy problem. And if you don't, it's a very hard problem. And the reason I'm mentioning that, it does come up every now and then. What do you take a derivative of to get secant squared? Tan of x. It's that simple. If you know that, I should use the identity. And it's very challenging if you don't. And here we are.